Your first year on the moon would be less giant leap and more daily fight not to fall apart. Your body is quietly breaking down in low gravity. Your air and water depend on experimental machines, and a few millimeters of metal are all that separate you from hard vacuum, radiation, and razor-sharp dust. There's no blue sky, no weather, no way to step out alone, only a small crew, a half-built base, and a hostile world that punishes every mistake. In this video, we're going to unpack why that first year is the most fragile, dangerous, and revealing test humanity will face on another world. You think the hardest part of living on the moon is the vacuum or the radiation. The first real shock is much simpler, just trying to stand up in the morning. The second you leave Earth, the basic rules your body has used for your entire life stop working, and nothing about that feels heroic. It just feels wrong. You've lived every second so far at about 1g of gravity. That's roughly 9.8 meters per second, around 32 feet per second. On the moon, the pull is about 1.62 meters per second, close to 1/6 g. If you weigh 90 kilograms on Earth, about 200 pounds, on the moon, the scale would show only 15 kilograms, around 33 pounds. That number sounds exciting. You feel light, you can jump higher, you can lift heavy tools that would be a problem on Earth. But your body is not built for that change. Every muscle fiber, every tendon, your spine, your hips, your knees, have all been calibrated for a lifetime of pushing against 1g. Your brain has learned, without you thinking about it, exactly how much force to use when you take a step, sit in a chair, or lean on a wall. Drop that to 1/6 g and those automatic settings are suddenly wrong. You push off too hard, you overshoot. You can't trust your own movements. Apollo astronauts, after only a few days, were already stumbling and doing that strange hopping gait because normal walking failed. You're not there for a few days, you're there for a year. That means every simple movement is not normal life anymore. It's training, constant, tiring training. But gravity is not only about how heavy you feel, it is also how your brain knows which way is up, how fast you are moving, and whether you're about to fall. Inside your head, just behind your ears, are tiny tubes and chambers filled with fluid. This is your vestibular system. It senses rotation, tilt, and acceleration. On Earth, that system and your eyes agree almost all the time. When you stand, the fluid settles in a certain way. When you turn your head, it moves in a pattern your brain has seen since you were a baby. On the moon, the pull on that fluid is weaker. The signals your vestibular system sends no longer match what your brain expects when you move. Your eyes say, "I'm standing in a room. The floor is flat. I'm fine." Your inner ear says, "The pull on this fluid is different. Something is off." Your brain treats that conflict as a threat. The result is motion sickness, nausea, dizziness, headaches, and a general feeling that the world is unstable. NASA already sees this in orbit and calls it space adaptation syndrome. Many astronauts feel miserable for the first few days in altered gravity. In your first year on the moon, you don't have the luxury of lying down and waiting it out. You still have to work inside the base, you still have to go outside in a suit, you still have to trust your balance while standing on a rocky surface with sharp edge and life support systems around you. And while your balance system is arguing with your eyes, another quiet but serious change is happening. Your blood stops behaving like it did on Earth. Under 1g, gravity constantly pulls blood toward your legs. Your heart and blood vessels fight that pull to push enough blood back up to your chest and brain. Your body has pressure sensors and hormone systems tuned to that fight. In low gravity, that balance breaks. With much less downward pull, more fluid shifts toward your upper body and your head. Astronauts report puffy faces, stuffy noses, and skinny bird legs. It looks funny in photos, but it is a real medical issue. Extra fluid in your head changes the pressure inside your skull and behind your eyes. On the space station, this fluid shift has been linked to a problem where the shape of the eyeball changes and vision gets worse during long missions. On the moon, you live in a constant partial version of that state. Your heart may slowly remodel because it doesn't have to work as hard against gravity. Your blood pressure control can drift. Standing up quickly might make you faint. You could develop blurred vision or headaches that don't go away. During that first year, doctors on Earth will be staring at every blood test, every eye scan, trying to understand what 1/6 G really does to human circulation. You're not just a resident, you're the first full-time data point. Now, add another layer. While your fluids are shifting upward, the hardware that holds you up starts to weaken. Your body is efficient and ruthless. If you don't load your bones and muscles enough, it decides you don't need them. In weightlessness, astronauts can lose 1 to 2% of bone density per month in key areas, like the hips and spine if they do not use strong countermeasures. Large muscles in the legs and back shrink fast when they are not pushing against gravity. Even with hours of exercise each day, some loss still happens. On the moon, you are not floating, but 1/6 G is still far below what your skeleton evolved for. Walking in low gravity feels easy, which is exactly the problem. Easy does not stress the bones enough. Without extra load, heavy suits, weighted vests, strong resistive exercise, your body starts to break bone down faster than it builds it. Over a year, that can mean serious loss of strength and density. Joints may change, cartilage may wear in new ways, and your risk of fractures grows. Muscles also adapt downward. If your daily tasks do not push them hard, they will quietly shrink. Early crews will have treadmills and resistance machines to protect bone. But these systems are not yet perfectly tuned for 1/6 GT. How long, how hard, how often should you train? That is still being figured out. So your first year becomes a constant battle between your schedule, science, maintenance, construction, repairs, and the minimum amount of exercise you must do just to avoid coming home with the bones of someone decades older. Even if you somehow keep that strength, there is one more brutal twist. The way you move still doesn't make sense, because mass and weight play by different rules. Your weight on the moon drops to 1/6, but your mass stays the same. Mass is what resists acceleration, what makes it hard to start or stop moving. In everyday speech, your body is just as hard to stop as it was on Earth. So when you push off the ground, you feel light and powerful, but your body and your life support backpack still carry the same momentum you had back home. You accelerate more easily because you weigh less. But once you are moving, stopping is just as demanding as before. This is why Apollo astronauts kept falling. A small misstep, a slightly too strong push, a twist at the wrong moment, and their body and backpack kept going when their feet did not. On the moon, falls look slow because gravity pulls you down more gently, but the impact can still be serious. You hit rocks, you hit the ground, your suit takes the force. A cracked visor, a damaged joint, or a torn glove is not a minor injury. It is a direct threat to survival. Now, stretch that risk across a full year. You're doing spacewalks to set up solar panels, to bury cables, to build radiation shields from regolith. You go outside over and over, sometimes tired, sometimes stressed, sometimes not fully recovered from yesterday's work. Inside the base, even moving down a narrow corridor or climbing into your bunk has to be relearned. There is no normal walk anymore. There is only the walk that does not make you fall, the turn that does not spin your pack, the push that does not send you drifting into something sharp. So in your first year on the moon, your own body becomes your main enemy and your main unknown. Gravity drops, your balance system fights you, your blood moves uphill, your bones and muscles try to fade away, and basic movement becomes a constant test. All of that is happening before you even think about the outside world. And that brings up the next problem. While your body is struggling just to adapt, the place you live is separated from a hard vacuum by only a few millimeters of metal and plastic. When breathing itself depends on machines that have never run this long on another world, how safe can you really feel? You're never more than a few millimeters of metal and plastic away from your blood boiling in a vacuum. That is not drama. That is the basic fact of living on the moon. Outside your habitat, the pressure at the surface is so close to zero that it might as well be empty space. There is no air you can breathe, no outside you can escape to. The wall of your module, maybe a few centimeters thick, is the only thing stopping every gas inside your body from shooting outward at once. On Earth, If something goes wrong with the air in a building, you get outside. You open a window, firefighters break a door. On the moon, outside is worse than any burning room. History already shows how unforgiving this is. One cabin fire on the pad like Apollo 1, and the crew has no time to escape. One leak in a spacecraft like Soyuz 11, and everyone is gone before they can put on suits. Your first year on the moon is when life support hardware is new, seals are new, software is new, and there is very little long-term data on how any of it behaves under real lunar conditions. You are trusting your life to systems that have never run this long, in this gravity, under this thermal stress, this far from help. If the shell around you is that fragile, the obvious question is, why not just bring a huge supply of air from Earth and overbuild everything? Because the math crushes that idea very fast. One person uses close to 0.84 kilograms of oxygen every day, almost 2 pounds. That same person exhales around 1 kilogram, a little over 2 pounds, of carbon dioxide every day. With 4 people in your base for 1 year, that adds up to more than 1,200 kilograms of oxygen and over 1,400 kilograms of carbon dioxide you have to deal with. That is more than 2.5 metric tons of gases to bring, store, and somehow handle just for breathing. Launching that mass from Earth is extremely expensive. You are not sending a few scuba tanks, you are talking about several small cars worth of gas by weight. And that is only for your lungs, not for fuel, not for cooling, not for leaks, not for emergencies. So instead of a simple bring everything plan, you're forced into something much more fragile. Closed-loop systems. Machines that split water into oxygen and hydrogen. Systems that grab carbon dioxide out of the air and convert it into other chemicals. Filters that can be heated to release trapped CO2 and used again. These are clever, advanced technologies. Electrolysis units, Sabatier reactors, solid amine beds, and more. They are also complex and they fail. A pump breaks, a catalyst gets poisoned by a trace impurity. A sensor slowly drifts out of calibration. In a normal building on Earth, if the air system goes down, you have hours, maybe longer, and you can open doors. On the moon, if oxygen production stops or CO2 removal stalls, you start a countdown. You watch partial pressure numbers creep in the wrong direction, and you know that beyond a certain point, no amount of heroics will help. Your first year is when these recycling systems stop being lab hardware and become life support for real. And you are the one standing next to them, listening for strange noises. It is easy to focus on oxygen as the main thing you need. But inside a closed habitat, the real threat often comes from what you exhale and what silently leaks out of your own equipment. Carbon dioxide is the classic quiet killer. At sea level on Earth, the amount of CO2 in the air is tiny. In a sealed module, it rises quickly if removal systems lag even a little. NASA keeps CO2 on the space station under a tight limit because higher levels cause headaches, confusion, and poor decision-making long before you pass out. That is the last thing you want in a crisis, and the gas does not always mix evenly. In a small lunar base, if fans are not placed and tuned correctly, you can get pockets of higher CO2 near the floor, in corners, or in sleeping areas. You can be lying in your bunk, breathing air that is subtly worse than what the sensors in the main cabin are reading. Then there are the trace contaminants, ammonia from cleaning fluids, alcohol vapors from disinfectants, compounds that slowly come off plastics, sealants, adhesives, paints, electronics. On Earth, most of that drifts away into a huge atmosphere, or gets diluted to harmless levels. In your lunar base, all of it stays inside the same limited volume of air, going through the same filters over and over. Your own body is a source of chemicals too. Sweat, skin particles, metabolic byproducts. The longer you stay, the more this invisible mix builds up unless filters and scrubbers catch it. Your first year becomes a constant unseen battle against molecules you never think about on Earth. Every new piece of equipment you unpack could be adding a chemical you did not plan for. Even if the air inside is clean for now, you still have another problem. keeping that air from slowly leaking away into space. No pressure vessel is perfectly tight. On the space station, tiny leaks are normal. You might lose a few hundred grams of air a day, less than a pound, and still spend weeks trying to locate the exact spot. On the Moon, your base might use rigid metal modules, inflatable sections, or shells 3D printed from lunar soil. All of these are new designs being tested in a real environment for the first time. Seals dry out. Thermal cycling from the brutal lunar day and night makes structures expand and contract. Micrometeoroids, basically high-speed grains of sand from space, slam into exposed surfaces and can punch pinholes you cannot see. So every day someone checks pressure trends. Is the cabin pressure slightly lower this week than last week? Is that drop just from airlock use? Or is there a slow leak hiding in a joint, a valve, or a wall? Finding it might mean hours or days of closing off sections, listening with sensors, spraying areas with special foams that react to escaping air. During that first year, you do not yet fully know how your particular habitat design ages in this environment. You are learning that in real time, breathing the air that is always trying to leave you. And while all of this is happening, there is one more layer that is hard to see but impossible to avoid. You are constantly breathing the history of your environment. In a closed system, nothing truly disappears. A cleaner you used 3 months ago may still have traces looping around in the air. A minor coolant leak from a piece of equipment might leave chemical fingerprints in the filters long after the hardware is repaired. Add lunar dust to that, fine sharp particles that get inside despite every protocol, carrying with the minerals and metals your lungs never evolved to handle. New construction materials, especially 3D printed regolith structures, might release gases under heat or radiation that no one fully predicted during tests on Earth. So every breath in year 1 is also a sample of every design decision and every shortcut anyone ever took in building your base. If a plastic outgasses something toxic at low levels, you find out by headaches, rashes, coughing, or blood tests that start to drift. If a certain sealant breaks down under radiation and heat, you learn that from the taste of the air, from eye irritation, from strange readings on chemical sensors. Later crews will benefit from your data. They will use safer materials, better filters, smarter layouts. You are the one who learns which parts were a mistake the hard way, through your lungs and your bloodstream. So your first year on the Moon is spent inside a thin shell that is always leaking a little, filled with recycled air that is always a few system failures away from danger, slowly loaded with chemicals you cannot see. Every breath depends on machines that were never meant to be perfect on the first try. And all of this pressure just to stay alive is still happening before you even step outside to deal with the radiation, the dust, and the temperature swings waiting for you there. If simply taking a safe breath costs this much effort, what happens when the gravity itself starts attacking your skeleton, your muscles, and even your heart over months and years? You can stand on the Moon, you can drop a tool and watch it fall, and that simple fact tricks you. Zero gravity feels alien immediately. 1/6 G feels almost normal. That is the danger. Your brain sees a flaw, sees objects falling, and quietly decides, this is fine. Meanwhile, the actual force going through your bones and joints has dropped to a fraction of what they need to stay strong. You feel okay, so you don't feel the urgency. You skip a workout here, take a lighter load there, shave a few minutes off the treadmill because you're tired. By the time you notice real weakness, damage is already done. So what does that drop in loading actually do to your skeleton over time? On the space station, in almost zero gravity, astronauts can lose 1 to 2% of bone density per month in key areas, like the hips and spine if they do not follow strict countermeasures. Even with intense training, some still lose around 0.5 to 1% per month. Over a year, that adds up to 6 to 12% loss in the places that hold you up and protect your spinal cord. That is like making your skeleton age by a decade or more in just one mission. Muscles in the legs, back, and core also shrink if they are not loaded hard. You can literally see it in before and after scans and strength tests. This Moon's 1/6 G should slow this down compared to full weightlessness, but the keyword is should. We do not have long-term human data in partial gravity. Nobody has lived for a year at 1/6 g. Maybe you lose bone at half the orbital rate. Maybe it is only slightly better. Maybe certain joints, like knees and ankles, suffer more because the pattern of stress is strange. You are lighter, but you still twist and land in ways your cartilage did not evolve for. Your first year on the moon is when those curves get drawn for the first time. When you get back to Earth and stand in a scanner, doctors will see exactly how much skeleton you paid for that 1 year. If the only answer was do more exercise, that would be hard but simple. The problem is that exercise itself becomes almost a second full-time job. Right now, astronauts in orbit spend about 2 hours every day on structured workouts, not counting setup and cleanup. That is heavy resistive exercise to simulate weightlifting, plus cycling or treadmill running with harnesses to pull them against the machine. That is just to return home able to walk up a short set of stairs without collapsing. On the moon you may need at least that, maybe more, because gravity is not gone, it's just weak. Some muscles will still work during daily tasks, and others will be underused. Standing and moving in 1/6 g might protect some areas a little, but leave others almost unloaded. The hardware will be early generation gear, treadmills that have to work in low pressure or full vacuum areas, resistance machines redesigned for partial gravity, maybe a small centrifuge that spins you to create brief periods of higher effective G. None of this will be as polished as gym equipment on Earth. It will break. It will need constant maintenance. Straps will dig into your shoulders because they must pull you down to mimic your Earth weight. Maybe 80 kilograms, around 180 pounds, even though your lunar weight is around 13 kilograms, about 30 pounds. So your daily schedule starts to look brutal. Work shift in the lab or repairing equipment outside, then straight into an intense training block just to slow down bone and muscle loss. Then food, then sleep, repeat. Skip too many sessions because you're busy or exhausted and you're not just out of shape. You're increasing your risk of fractures, joint problems, and long-term disability. While your skeleton is thinning, your heart is quietly remodeling too. On Earth, your heart works against 1 g all the time, pushing blood up from your legs to your chest and brain. In microgravity, that load drops suddenly. At first, more blood shifts to the upper body, and the heart can look a little enlarged. Over time though, because it does not need to fight gravity as much, the heart muscle can lose mass. Stroke volume, how much blood it pumps with each beat, changes. Some astronauts come back with hearts that are physically smaller and less prepared for standing in 1 g. Partial gravity on the moon sits between Earth and orbit, but we do not yet know exactly where in terms of heart effects. Maybe your heart shrinks more slowly. Maybe the fluid shifts are less extreme. Maybe some parts of the cardiovascular system adapt in a way we have not even modelled. The scary scenario is this. You live years in low gravity, your body adjusts to that as the new normal, and then you suddenly need 1 g again for emergency medical treatment back home. Your heart, your blood vessels, your reflexes that keep blood going to your brain when you stand, all of them might be underprepared. Fainting, dangerous drops in blood pressure, irregular rhythms, these become real risks. In that first year, every ultrasound, every MRI, every treadmill test in your base's tiny medical bay becomes part of a new medical field. What a 1/6 g heart looks like, and whether it can handle coming back to Earth's full pull. We are not going into this blind. There are already ideas on how to fight bone and muscle loss and protect the heart. But every one of those ideas is still an experiment. There are vibration platforms that shake your body at specific frequencies to stimulate bone. There are plans for short radius centrifuges, basically spinning chairs or beds that create higher effective gravity at your feet than at your head, trying to load the skeleton without spinning the whole base. There are detailed diet plans with extra calcium, vitamin D, and specific proteins to support bone and muscle, while also trying to avoid kidney stones, which are more likely when your body dumps extra minerals into urine in low gravity. All of these countermeasures are promising, but they are not mature. Most have been tested in small studies, in microgravity or ground simulations, for months, not years. As a first-year lunar resident, you are both the patient and the test subject. You might be strapped into a spinning machine that makes you feel strange, but might save your hips from collapsing 10 years later. Your meals are not just meals, they are part of a controlled plan to keep your skeleton and your heart alive in an environment they never evolved to handle. So under 1/6 G, your bones can quietly thin, your muscles can shrink, your heart can slowly remodel, and your daily life gets squeezed between mission work and physical survival routines. That is the slow breakup with your own skeleton. It does not happen in one dramatic moment. It creeps forward day by day, number by number, scan by scan, and this entire physical struggle plays out under a sky that never turns blue, with days and nights that last for weeks. If the gravity is grinding down your body this slowly, what does that stretched alien sense of time do to your sleep, your mood, and your mind? How do you keep a 24-hour body clock running on a world where a single day lasts almost a month? On the moon, the ground beneath you turns once every 27.3 Earth days, and relative to the Sun, a full lunar day-night cycle takes about 29.5 days. That means close to 2 weeks of daylight, then 2 weeks of darkness at the equator. Your internal clock, though, runs on roughly 24 hours. Your genes, your hormones, your temperature rhythm, your hunger, your alertness cycles are all built around a day that resets with every sunrise and sunset. The moon takes that external reset away. On Earth, your circadian rhythm uses light and darkness as hard signals. Morning light tells your brain to shut down melatonin, the hormone that makes you sleepy. Evening darkness tells it to ramp melatonin up. You see the sky change colour. You feel temperature dip at night. Even if you never think about it, that 24-hour pattern is burned into you. On the moon, there is no blue sky. During the long day, the sun just hangs in a black sky for about 14 Earth days straight if you are near the equator. During the long night, there is no gentle dusk, just a plunge into shadow and cold that lasts another 14 days. Your body is still trying to run on 24 hours, but the outside world is screaming 29.5 days at your eyes. So you try to break that link and fake an Earth day inside the habitat. Inside the base, you live by the clock, not by the sun. Lights switch on and off on a strict 24-hour schedule. Morning sunrise is a row of LEDs shifting to a cooler, bluer colour. Evening sunset is warmer, dimmer light. You eat breakfast, lunch and dinner by the schedule, not by looking outside. Sleep periods are enforced. Meeting times and work shifts mimic a normal Earth day as much as mission control can manage. On the space station, tunable lighting like this has already helped crews sleep better. On the moon, it becomes your only real day-night signal. But your brain is not stupid. It knows, at some level, that outside the hatch the sun has been in the same part of the black sky for 10 Earth days straight, or that the landscape has been in total darkness for a week with only your floodlights cutting it. If you glimpse outside during a night period, inside your eyes see bright sunlight. If your base sits near a pole for better power and temperature, the sun may just skim the horizon constantly, never doing the clean rise and set your inner clock wants. You're asking your biology to ignore every external cue and trust a set of bulbs and alarm clocks instead. That would be hard even if you felt completely safe. You don't. Even in low Earth orbit, astronauts sleep worse than on the ground. They report shorter sleep, waking up more often, strange dreams, and more frequent use of sleeping pills. On the moon, you add layers of threat. You know that radiation levels are higher than on Earth. You know that a micrometeoroid hitting the wrong spot in the wrong moment could punch a leak. You know that your air, water, and power all depend on machines that can fail. Apollo astronauts, during their short stays on the lunar surface, did not sleep deeply. They described light, broken sleep, always half listening for alarms. Now stretch that feeling across 365 nights. You try to go to bed, but your mind is running through checklists. Was that pump a bit louder today? Did the CO2 scrubber just cycle more often? Did we log that pressure drop in the airlock? You wake up for system checks. You get up early for an EVA that has to match a window when mission control is awake on Earth. You adjust to other crew members moving around in a cramped space. You add up small sleep losses night after night. Over time, you build a chronic sleep debt. Slower reaction times, worse memory, more mistakes. In an environment where one mistake can cascade into an emergency, that is not just uncomfortable, it is dangerous. Poor sleep would be easier to fight if the outside world felt rich and alive. It doesn't. You look out the window and the view barely changes. No clouds, no blue, no storm rolling in, no green plants, no animals. Just grey rock, black sky, stars that don't twinkle because there is no air, and a sun that either blasts or is gone. On Earth, even a quiet day has birdsong, wind, distant traffic, colour. Your brain is used to background variety. On the Moon, the background is almost the same every single time you look. Antarctic bases already show how harmful that kind of monotony can be. People there, cut off for months, often develop winter-over symptoms. Low mood, irritability, trouble focusing, a sense of mental fog. Your lunar base is even more cut off. In Antarctica, you can still breathe the air outside. In an emergency, a rescue plane might come in months, not years. On the Moon, outside is vacuum. Rescue is not fast. The crew is tiny, maybe 4 to 10 people. When the excitement of "we're on the Moon" wears off, what you are left with is a small group, a metal shell, repeated tasks, and an empty landscape. The hardest point is not the first week, when everything is new. It is around the middle of that first year when the novelty is gone, but the danger has not dropped. You realise this is not a trip. This is just your life now, and that can hit hard. Under those conditions, your sense of time itself starts to bend. Stress makes time feel slow. Boredom also makes time feel slow. Repetition makes days blend. You get all three at once. Your daily schedule is full. Check systems, repair gear, run experiments, log data, clean filters, exercise, talk to mission control, do medical checks. Some of these tasks are interesting. Many are not. All of them matter. So your brain tracks them as effort, not as variety. A 6-hour maintenance block in a cramped equipment bay under harsh white light feels longer than 6 hours of mixed activities on Earth. At the same time, weeks can blur together because there are very few strong markers. No weather shifts to break the pattern. Limited chances to celebrate things like holidays the way you would at home. A weekend might just be a day with only critical tasks plus exercise. When you talk to people on Earth, their seasons change, their daylight length shifts, their local news cycles move on. For you, day 120 and day 220 might look and sound almost identical outside the window and inside the habitat. The clock on the wall says only a week has passed. Your nervous system says it's been much longer. To keep an eye on that, the mission will build in constant psychological monitoring. Regular check-ins with specialists on Earth, simple computer tests that measure your reaction time, attention and memory, mood surveys, sleep tracking, heart rate and stress hormone data. You might feel fine, but the data could show you are slowing down, or missing more details, or drifting toward depression. The problem is that you cannot just walk away or take real time off or step into a park and reset your senses. You are stuck with the same walls and the same sky while being asked to keep making sharp, life-critical decisions. So during your first year on the Moon, your body clock fights a 29.5-day environment with a 24-hour rhythm. Your sleep is shallow, your view is lifeless, your days feel heavier than the clock says they are, and your mind has almost no natural way to recover from stress. You're trying to stay mentally stable in a place that strips away nearly every cue your brain uses to feel normal. And above all of this, while you are tired, stressed, and staring at the same dead horizon, there is something else you cannot see. A continuous rain of high-energy particles quietly passing through your body, changing your cells one hit at a time. If your mind is already stretched by broken days and a black sky, what happens when you add a slow, non-stop radiation dose to every organ you have? You grow up inside Earth's protection without ever noticing it. The planet's magnetic field and thick air block most of the high-energy particles streaming in from the sun and from deep space. On the Moon, none of that protection is there. There is no global magnetic field, almost no atmosphere, and nothing between you and those particles except whatever shielding you bring with you. Measurements from lunar missions show that radiation at the surface can be 2 to 3 times higher than what astronauts see on the space station, and roughly 150 to 300 times higher than the natural background at sea level on Earth. You're standing in a place that space agencies currently treat as a high radiation work site, not a safe neighbourhood. The numbers look small on paper, but they build up fast. During the Apollo missions, dosimeters worn by astronauts recorded around 1 to 3 millisieverts of radiation per day on the surface during short stays. On the International Space Station, the typical rate is about 0.5 to 1 millisievert per day. On Earth's surface, you get roughly 2 to 3 millisieverts in an entire year from natural background sources, so one day on the Moon can give you about the same dose as several months on Earth. Stretch that over a year and it becomes serious. Even with some basic shielding, a first-generation lunar base could still expose you to 300 to 500 millisieverts in 12 months. To give a sense of scale, many space agencies set career limits for astronauts in the range of a few hundred to maybe 1,000 millisieverts total, depending on age, because above that, lifetime cancer risk rises sharply. 1 year on the Moon could eat up a big fraction of that budget in a single tour, and that assumes no major solar storms. Most days, the radiation you get on the Moon comes from a constant background of galactic cosmic rays and a steady flow of particles from the Sun. These damage your DNA slowly, one hit at a time. The real danger spike comes from solar particle events, big bursts of high-energy protons from the Sun when it erupts. In a strong event, you can receive in a few hours the dose you would normally take months to collect. In 1972, between Apollo 16 and Apollo 17, the Sun produced such a storm. If astronauts had been on the lunar surface in simple suits then, models suggest they could have received a dose high enough to cause acute radiation sickness or worse. Because of that, your base must have a dedicated storm shelter. This is a space surrounded by extra shielding, thick layers of water, hydrogen-rich plastic like polyethylene, or piled lunar soil. When solar monitors and satellites see the first signs of a flare or a coronal mass ejection, you drop what you're doing and get into that shelter. You might stay there for many hours, possibly days, until the flux drops. In your first year, you do not know yet how often this will happen in practice at your exact location, or how disruptive each event will be. You are living through the early statistics. You might pass a quiet year. You might be unlucky and get a once-in-a-decade storm in month 3. Radiation is not just about cancer decades later. The particles that worry you most in deep space and on the Moon are high-energy ions with high linear energy transfer, often called high LET particles. They do not just nick DNA, they cause clusters of breaks and complex damage that cells find hard to repair. Animal studies under simulated cosmic radiation show changes in brain function, including memory and learning problems. There are signs of increased risk for cardiovascular disease and damage to blood vessels and the heart. There are effects on the immune system, making infections or reactivation of dormant viruses more likely. At high enough doses or with poor shielding, day to day you might not feel anything obvious. No burning, no glowing, nothing like that. But your medical team will be tracking this constantly. Regular blood draws to watch for changes in white cell counts and markers of DNA damage. Eye exams to look for early cataracts, which can be driven by radiation. Hormone checks. Cognitive tests to see if your reaction times or memory are slipping faster than expected for someone your age. Every reading from your personal dosimeter, a small device that measures your accumulated dose, gets logged and compared against models. In that first year, those models are being updated using your data. To cut the dose, you rely on mass. Radiation shielding is very simple in one sense. More material between you and space is better. Studies suggest that around 5 to 10 grams of material per square centimetre can significantly reduce the dose from many types of space radiation. That is equal to about 5 to 10 centimetres of water, roughly 2 to 4 inches, or about 20 to 30 centimetres of lunar soil, roughly 8 to 12 inches. Water and materials rich in light elements like hydrogen are especially good at slowing down protons. Thick layers of regolith help against many particles, though they can also generate some secondary radiation, so design matters. Because moving mass from Earth is extremely expensive, early lunar bases will try to use local material. That means you will use robots or crewed vehicles to shovel and dump regolith over habitats, building up a protective blanket. You might store water tanks and fuel around sleeping areas to act as extra shielding. You may design internal layouts so that you sleep and spend off-duty time in the most protected zones, and only accept higher exposure when you move closer to outer walls for work. Here is the catch. In year 1, a lot of that shielding will not be in place yet. You arrive to thin-walled modules delivered by rockets. The regolith berms are still small or not built. The best shielded rooms might still be under construction. Power limits might restrict how much you can run the heavy digging equipment. EVA time spent outside in a suit with even less protection, is highest in this period because you are assembling everything. That means the highest effective radiation doses of your whole lunar career will probably come in this first construction year, when you are also the busiest and most stressed. So during your first year on the Moon, you live in a place with no magnetosphere, almost no natural shielding, and radiation levels that can match months or years of Earth exposure in a matter of days. Your long-term health risk goes up with every shift. Your short-term risk can spike in a single solar event, and the heavy protection you need is still being built around you, while the cosmic rays and solar particles keep coming. Radiation is invisible and silent, but there is another threat that is brutally obvious the moment you look at a temperature chart. A world that swings from extreme heat to extreme cold by hundreds of degrees, over and over, while your thin habitat tries to hold a narrow band of room temperature in the middle. If the sky is already dangerous, what happens when the ground beneath you turns into a huge thermal stress machine for every bolt and seal you depend on? How do you keep anything working on a world where the ground cycles between blast furnace and deep freezer every month? At the Moon's equator, surface temperatures during the long day can climb to about plus 120 degrees Celsius, around 250 degrees Fahrenheit. During the long night, they can drop to roughly minus 170 degrees Celsius, about minus 274 degrees Fahrenheit. That is a swing of almost 300 degrees Celsius, more than 500 degrees Fahrenheit every lunar cycle. Metals expand and contract with that. Seals flex and relax. Electronics see temperatures far beyond what most devices on Earth ever face. You're trying to build a precise life support machine on top of a giant thermal torture rack. Your habitat has to ignore all of that and hold a narrow comfort zone, maybe 20 to 24 degrees Celsius inside, around 68 to 75 degrees Fahrenheit. That means the walls, radiators, pipes, and pumps have to constantly move heat in and out to keep you there. When the sun is high and the ground around your base is baking, you have too much heat. You need to dump it into space using radiators that glow infrared out into the vacuum. When lunar night falls and the outside drops toward minus 170, the problem flips. Now you have to keep precious warmth inside and use heaters to stop pipes, batteries and lines from freezing. On the International Space Station, a huge amount of power and engineering effort already goes into thermal control, and that is in low Earth orbit where sunlight and shadow alternate every 90 minutes and temperatures are tamer. On the Moon, the day and night last about 14 Earth days each, and there is no atmosphere to smooth anything out. Radiators can only throw heat in one direction. Heat pipes and coolant loops run through your base, carrying waste heat from electronics, people, and machinery to panels exposed to the sky. Phase change materials may melt and solidify to buffer sudden changes, and all of this has to work while fine lunar dust tries to coat radiators, insulate surfaces, and change how efficiently they emit heat. Then there are the cold traps near the poles, which are both gold mines and death zones. In permanently shadowed craters, sunlight never reaches the floor. Temperatures there can fall below minus 230 degrees Celsius, around minus 382 degrees Fahrenheit. At those temperatures, water vapor and many other gases that would boil away at the equator stay frozen solid for billions of years. That is why these craters are so valuable. They likely hold ice and other volatiles you can use for water, air and fuel. but the same conditions that preserve those resources also wreck equipment. Metals become more brittle. Many lubricants used in bearings and joints stop flowing or freeze. Plastics and rubber harden and crack. Battery performance collapses in that kind of cold unless you keep them heated, which costs power you may not have. Your first-year missions to scout and sample these regions will push rovers and drills into environments even harsher than the already bad normal lunar night. Models and lab tests on Earth can only go so far. The first time you drive a vehicle down into a permanent shadow at -230, you are finding out in real time how close to failure the design really is. Even away from the poles, just moving through normal lunar days and nights beats up your hardware. Every dawn on the moon, as sunlight starts hitting your structures, they warm up and expand. Every sunset, they cool and contract. Long runs like solar panel arrays, antenna masts, walkways, and external piping do this breathing over and over, each cycle adding a tiny bit of fatigue. On Earth, bridges and rail lines have expansion joints to handle far smaller temperature swings. On the Moon, you're asking joints, welds, bolts, and composite materials to survive hundreds of degrees of change, with no air around to share or smooth that heat. The first year is when you discover what was under-designed. Maybe a radiator panel warps slightly and no longer points where it should. Maybe a seal between two modules starts to leak because repeated expansion and contraction have opened microscopic gaps. Maybe a cable conduit delaminates, peeling layers apart so dust can get in, and moisture from your internal atmosphere can condense and freeze. You will have strain gauges, temperature sensors, and inspection routines built into the base, but those are still prototypes too. You are mapping where real cracks and hotspots appear on an actual lunar structure for the first time. All of this also hits you personally every time you go outside. Your body normally controls temperature by sweating and by moving blood closer to or farther from your skin. On the Moon, in a suit, that does almost nothing. There is no air outside to carry heat away by convection, and your sweat cannot evaporate into a vacuum. Left alone, you would quickly overheat inside the suit just from your own metabolism and muscle work. So the suit carries its own small thermal control system. Under the outer layers, you wear a liquid cooling garment, a network of thin tubes that run water around your body to pick up heat. That warm water flows to a device, maybe a sublimator that dumps heat by turning ice into vapor in the vacuum, or a tiny radiator loop that throws that heat away into space. Pumps, valves, sensors, and controls have to keep that loop in the sweet spot. Too much cooling and you start to chill, too little and you slowly cook in your own sweat. When you're working hard in the sun, drilling or lifting or walking long distances in 16G, the system has to suddenly handle as much heat as a long run on a hot day on Earth, but with no outside air to help. These systems are delicate and complex, and lunar dust plus extreme temperature changes make them worse. Dust can clog tiny channels or stick to radiator surfaces, cutting their performance. Repeated thermal cycling can stress solder joints and seals inside the backpack where your cooling gear sits. First-year operations will mean constant tweaks, changing how long EVAs can last, adjusting work-rest cycles, changing how much cooling water you run at different activity levels, swapping out components that do not stand up to the combination of heat, cold, and dust. Machines around you face the same fight. Electronics generate heat that has nowhere to go except into radiator loops. Batteries must stay within tight temperature ranges, or they lose capacity or fail early. Motors in external robots and rovers can burn out in the heat of lunar noon or stall in the cold of lunar night. Heaters to keep them alive draw power from solar panels and nuclear units that are themselves trying to survive temperature swings. Every watt you spend on heating or cooling a machine is a watt that you cannot use for scientific instruments, communication, or life support. So your first year on the Moon is a non-stop test of whether you can keep a small pocket of room temperature alive on a world that swings by hundreds of degrees over and over, while fine dust and harsh radiation slowly degrade the very systems you depend on. You are living inside a thermal compromise surrounded by hardware that is always on the edge of too hot or too cold. And that dust you keep hearing about does not just sit there. It grinds into seals, coats radiators, rides electric fields, and follows you back into the air you breathe. If temperature extremes are trying to break your machines from the outside, lunar dust is what sneaks inside to attack everything from your suit joints to your lungs. Lunar dust is not like dust in your house. It is not e-holed, it is not rounded, and it is not harmless. The soil on the moon is called regolith, and it is what you get when rock is smashed over and over for billions of years by micrometeorite impacts, with no air or water to smooth anything out. The particles range down to a few micrometers in size, smaller than pollen, and they're jagged, sharp fragments of rock and glass. Under a microscope, they look like broken shards, not grains of sand. Apollo astronauts said it clung to everything and even had a smell when they brought it into the cabin, something like burnt gunpowder. That smell came from how chemically reactive those fresh broken surfaces are when they suddenly meet oxygen and moisture in your air. On a short Apollo mission, that dust was an annoying problem. On a 1-year mission, it becomes one of the main enemies of your equipment and your health. During Apollo, dust worked its way into suit joints and bearings, making them harder to move and wearing them down. It jammed zippers, it abraded seals. In at least one case, it fouled a drill enough to affect its performance. Astronauts tracked it into the lunar module on their suits and boots, where it floated in the cabin's low gravity. They breathed it. They got red, irritated eyes and stuffy noses. They called it lunar hay fever. Now scale that from a few days to 365 days. Every time you go outside, you stomp around in this powder of microscopic glass knives. It packs into the tread of your boots, into gaps in your suit joints, into tool handles, into equipment housings. When you come back in, you bring some of it with you, no matter how careful you are. Air filters inside the base load up with fine particles. If any of that dust bypasses the filters, maybe through a small leak or during a suit removal, you and your crewmates inhale it. This is no longer a short-term respiratory irritation. It is a constant, low-level inhalation risk. At the same time, the abrasive dust is grinding away at moving parts. Bearings in airlock doors, seals in connectors, sliding rails on equipment. Anything that moves and is not perfectly shielded is slowly being sandblasted. Dust on the moon also does not behave like dust on Earth because the whole surface is electrically active. Under sunlight, ultraviolet radiation from the sun and charged particles from the solar wind make the top layer of regolith gain or lose electric charge. That charging can cause dust grains to repel each other or be pushed along at electric fields. Near the boundary between day and night, the terminator, some models and measurements suggest dust can actually levitate and move, forming a faint haze just above the ground. The key point is that dust is not just sitting there waiting for you to step on it. It can float, jump and stick. Your base with its metal structures, cables and antennas will disturb electric fields around it. Surfaces can charge differently in sunlight and shadow. That means dust can be drawn toward the exact places you least want it. Radiator faces, optical sensors, thermal blankets, connector housings, and around airlock doors. Static cling, which is just an annoyance on Earth when your clothes stick together, becomes a serious engineering issue. You may have to ground structures, design special coatings, or build active dust-repelling systems just to stop every exposed surface from getting a layer of fine insulating dirt. Your lungs are tuned for a completely different kind of dust than this. On Earth, the particles you breathe are usually rounded, or at least softened by water and weather. They are mostly organic material, soot or mineral, that have been eroded. Lunar dust combines sharp physical shape with reactive chemistry. The fresh fracture surfaces can contain nanophase iron and metal oxides that react strongly when they meet water and oxygen. Studies using lunar simulants, Earth-made materials that mimic lunar soil, show that when this kind of dust touches lung cells, it can trigger inflammation and toxic responses. In the short term, that might mean coughing, irritation, and reduced lung function after exposures. Over a year, with repeated low-dose exposure, your risk profile grows. Chronic inflammation in the lungs can lead to scarring known as fibrosis. That stiffens lung tissue and cuts how much air you can move. Some mineral dusts on Earth are linked to increased cancer risk after long exposures. Lunar dust is not identical, but it is reasonable to worry it could have serious long-term effects. Your first-year medical records, lung tests, imaging, blood markers of inflammation, will be the first real data set on what Moon Miner's lung looks like in real humans living on the surface. Because of all this, fighting dust becomes a major part of your daily routine, not an afterthought. You cannot just wipe your feet and forget about it. Airlock procedures will be detailed and strict, brushing, vacuuming, and maybe using air jets or electrostatic tools to knock dust off suits before you ever open the inner door. Many designs aim to keep suits attached to the outside of the habitat in so-called suit ports, so you never bring the outer shell indoors at all. You climb in and out from the back, leaving the dirty exterior sealed to the outside. Floors, filters, and surfaces inside the base will need regular cleaning. You will inspect seals and moving parts for dust abrasion and replace components sooner than you would like. New technologies will help. Coatings that dust does not stick to as easily, electrostatic systems that push dust away from sensitive surfaces, better filters that trap ultrafine particles without wasting too much power. But when you arrive in year 1, none of this has really been proven in long-term real-world lunar conditions. You are the first real test. Protocols will change as you discover what works and what is a waste of time. You will probably spend more hours than you want each week just dealing with dust, cleaning, checking, logging and repairing. The first year is, by definition, the dirtiest year. You do the most outside construction, the most setup, the most unplanned EVA work as you fix early problems. That means more suit use, more time walking and working in the regolith, more chances for dust to invade systems and lungs. Later crews will benefit from more mature designs, better coatings, smarter airlocks, and thicker dust shields. You are the crew that finds all the weak points. By now, every step outside your habitat looks more dangerous. Abrasive dust chewing through your suit joints, charged particles attracting dirt to the worst places, hidden long-term risks building up in your lungs. And yet you still have to step out there almost every day to build, repair and explore, all while moving in a gravity field that constantly tries to trip you and slam that fragile suit into the ground. If the environment attacks you this hard just for walking around, what does it mean for the simple act of doing a job outside, carrying tools, using drills, hauling equipment, when one bad fall or one torn seal in 1/6 G could end everything in seconds? Step outside your habitat on the moon and walking is no longer automatic. In 1/6 G, your normal stride falls apart. Apollo crews found that a kind of lope or bouncing jog worked better than trying to walk heel to toe, but they were only out there for a few days. You're doing this for a year. Every time you go out to fix a solar panel, check a sensor or move a cable, you're dealing with the same strange mix. Your weight feels low, but your mass and your suit's mass are still very real. Take a step and your body wants to bounce. Your muscles are still wired for 1G, so you push off harder than you need to. Because you're lighter, you launch higher and farther than you expect. But your life support backpack, maybe 80 kilograms worth of mass including you and gear, around 175 pounds, keeps moving exactly as physics says it should. When you try to stop or turn, you feel that pack tug and twist you. You're constantly correcting shorter steps, lower hops, wider stance, careful timing. It feels like slow motion parkour in a suit that was never designed for style, only survival. The slow motion is another trick. In 1/6 G, you fall more slowly, so your eyes and brain get extra frames to watch the ground coming up. That does not mean the impact is safe. Your mass is the same as on Earth, maybe 80 or 90 kilograms, 175 to 200 pounds. When you hit, the force still goes through your bones and joints. Apollo astronauts fell a lot. Tripped over rocks, snagged boots on cables, misjudged hops. They got away with scrapes, bruises, and scuffed suits because the missions were short and their bones were still Earth-strong. On a 1-year mission, your skeleton is already weakened by months of reduced loading. A fall that would have been a joke in training could become a fracture in your wrist, elbow, or hip. A bad landing on a rock could break a rib or crack a visor. Worst case, your suit takes a hit. A torn glove, a punctured joint, or a cracked helmet is not just an injury. It is a race against decompression, losing air into vacuum. Even a small leak adds deadly pressure on your crew. Patch it in seconds or minutes, or get back to the airlock fast enough, or that EVA becomes the last one. The tools you use and the way you use them have to be redesigned from the ground up because your weight, the thing you rely on to brace and push, is mostly gone. On Earth, if you want to drill into concrete, you lean on the drill. Your body weight holds it in place. On the Moon, if you lean the same way, you push yourself backward almost as much as you push the drill forward. Try to tighten a bolt with a wrench and you might spin yourself instead of the bolt. Even shoveling regolith is different. When Apollo engineers tried to use standard shoveling motions, they found astronauts just pushed themselves away instead of lifting useful loads, so they changed blade angles and techniques. For a long-duration base, every routine task has to be treated like that. Carrying buckets of regolith, laying cables, lifting instrument packages, deploying antenna masts. Everything needs new choreography and often new hardware. Handles, grips, and stabilizing brackets are designed so you can hook yourself in, push against something solid, and not launch yourself into a tumble. In your first year, many of these standard procedures are still informed guesses. You are the one who finds out that a certain way of carrying a tool bag always twists your center of mass the wrong way, or that a particular drill setup makes people lose footing. Every oops is logged and turned into a training note so the next EVA goes a little better. The fatigue that builds up from all of this comes from places you do not expect. Partial gravity sounds easy because you're lighter, but your stabilizing muscles, ankles, hips, lower back, are firing non-stop to keep you upright after every bounce and landing. Each correction is small, but over a 6-hour EVA, they add up. Pressurized gloves fight every finger movement, so gripping a tool or operating a control is like doing hand exercises with strong resistance the entire time. Your shoulders and forearms burn from working against that pressure. Your neck muscles strain to hold your helmet steady as your backpack shifts behind you. Inside, you already spend hours on a treadmill or resistance machine to slow bone and muscle loss. Outside, you add this strange jerky motion pattern on top. Some muscles get hammered daily just to keep you from tipping over, while others atrophy because they never see full 1G again. Overuse injuries build up in joints that never hurt on Earth, ankles sore from constant micro-landings, hips tight from always correcting your hop angle, lower back strained from fighting the suit in the pack. By the end of the day, you're exhausted in a way that does not match any Earth job. You are not lifting huge weights, but your nervous system has been running flat out just to keep you from falling in slow motion onto sharp rocks. All of this happens inside a thin layer of suit material that cannot tolerate endless abuse. Every EVA you do in that 1/6 G environment adds wear. Dust grinding at joints, thermal cycling stressing layers, small knocks and scrapes accumulating. The more you go out, the more chances there are for something to fail or for you to make a mistake. And in year 1, you go out a lot. The first crew does the most construction, the most setup, the most troubleshooting. Solar arrays have to be deployed and adjusted. Cables have to be buried. Regolith has to be moved over habitats for shielding. Antennas and sensors have to be carried to good locations and erected. Equipment will fail in ways no one predicted, and you will be the one sent out to fix it in person. Later crews will arrive to a base that is more complete with more automation, more robots taking over the riskiest outside work. You arrive to a to-do list that practically shoves you out of the airlock every day. EVA risk is, in the end, a numbers game. Suit hours add up. The longer you are out there, the more cycles your joints see, the more dust hits your seals, the more micrometeoroid exposure your visor and torso get. In the first year, there just has not been enough time for those risks to catch up with anyone yet, and you are the one multiplying your exposure faster than anyone who comes after. You're also doing all this in the phase when procedures are still being tuned, and human factors mistakes are most common. So just walking and working outside in 1/6 G means fighting unfamiliar motion, preventing slow falls that can still break weakened bones, wrestling tools that push you around more than the ground, and burning stabilizer muscles no one ever trained properly on Earth. You are learning how to move on the moon at the same time as you are betting your life on not messing it up. And while you burn through energy and suit lifetime doing that, there is another constant pressure in the background. Every drop of water you sweat, every calorie you burn, every breath you take has to be supplied, recycled and protected in a place with no natural safety net at all. If going outside to work is this risky, what happens when the basic supplies that keep you alive, water, food, air, are themselves right at the edge of what your fragile outpost can provide? On the moon, water is not just a supply item, it's one of the main reasons your base can exist at all. Water has a density of about 1,000 kilograms per cubic meter, roughly 2,200 pounds per cubic yard. Launching that much mass from Earth is brutally expensive. You cannot afford to treat water as disposable. In your first year, every drop you drink, every drop you use to wash, and every bit in your cooling loops is part of a tight budget that combines three sources: tanks shipped from Earth, aggressive recycling, and if you're based near the poles, early attempts to pull ice out of permanently shadowed craters. On the space station, current systems can recover about 90% of water from urine, sweat, and cabin humidity. That's already a complex chain of filters, distillation units, and chemical treatments. On the moon, that entire chain has to run under 1/6 GE, with dust always trying to get into seals and filters, and with more varied uses: cooling suits, industrial processes, maybe early construction methods that use water as a binder. If you're mining ice, now you add drills and heaters that must work at temperatures below -200 degrees Celsius, around -330 degrees Fahrenheit, then plumbing to move that meltwater into tanks without losing it to refreezing or leaks. Purification membranes can clog or tear. Distillation units can foul as minerals build up. Ice mining drills can jam in brittle, super cold ground. Every failure hits you twice. You lose water you thought you had, and you often contaminate or damage equipment you need. In year one, these systems are being pushed harder and longer than any test stand on Earth. You are the one watching flow meters and pressure gauges and wondering if today is the day a hidden crack turns into a real leak. Food looks simpler on paper, just send enough. In practice, it is a massive logistics and psychology problem. A typical adult needs on the order of 2,000 to 3,000 kilocalories a day. For a crew of 4 over 365 days, that's close to 3 million kilocalories. Even with compact high-density packaging that still weighs several tons. Think of at least a couple of family cars worth of mass. Most of it will be shelf-stable, freeze-dried meals, thermostabilized pouches, bars, powders. You add water, heat, maybe mix a few items, and eat from bags and trays. From ISS experience, you already know the catch: menu fatigue. Even with dozens of options, astronauts get tired of the same textures, the same smells, the same limited range of flavors. When that happens, they start eating less without really planning to. Weight drops, energy levels fall. If they consistently avoid certain dishes, they might also miss key nutrients tied to those foods. On the moon, where your body is already under stress from radiation and low gravity, undereating is a serious risk, not a small annoyance. Your first-year menus, storage layouts, and prep routines will all be experimental. How often can you rotate special treat foods to keep morale and appetite up? How do you store items so they don't get too much temperature cycling near walls exposed to lunar day and night? How much time can you realistically spend cooking or assembling meals when your schedule is packed with work and exercise? Each answer you find in year one changes how future cargo missions are packed. Because water and food are so hard to bring, your outpost is forced toward closed-loop life support. The basic rule is nothing leaves if you can avoid it. Your urine runs through treatment systems and comes out as drinkable water again. Your exhaled carbon dioxide gets pulled from the air. Some of it might be split and recycled into oxygen. Some of it might feed plants or algae in bioreactors, turning waste gas back into biomass and fresh oxygen. Early bioregenerative systems, algae tanks, plant modules, maybe small greenhouse racks, will likely be in test phases during your first year. They blur the line between support system and experiment. A tank of algae might help scrub CO2 and make oxygen, but if it crashes due to contamination or bad light levels, you suddenly have a goo problem and less life support capacity. A plant growth rack might produce a small percentage of your fresh food and do useful gas recycling, but it could also introduce mold spores or pests into the controlled environment if filters and protocols aren't perfect. Every time one of these systems hiccups, you feel it directly. You switch to backup filters, you tap into reserve oxygen, you eat into the margin of shipped food. Successes, on the other hand, are huge. Every kilogram of oxygen or litre of water you can reliably recycle locally is one you don't have to launch. In year one, you are not just using these systems, you are generating the data that will decide whether full closed loops are realistic for bigger bases or for Mars missions later. Your diet itself becomes a medical tool, not just a comfort. In low gravity, your bones are losing density. That pushes calcium metabolism out of balance. You need enough calcium and vitamin D to support bone, but your body is also dumping extra calcium into your urine as bone is broken down. That raises your risk of kidney stones, which are more common in astronauts. Stones are painful on Earth and dangerous in space where medical options are limited. So nutritionists and flight surgeons plan your food like a regimen. Sodium levels are controlled because high salt can worsen fluid shifts and blood pressure. Iron intake is watched because too much iron plus radiation stress might damage organs. Antioxidants from vitamin C and E and compounds like omega-3 fatty acids may help counter some inflammation and cardiovascular risks. You don't just have a snack, you follow a schedule. Blood tests, maybe weekly in year one, track electrolytes, vitamin levels, bone turnover markers. If a marker goes the wrong way, your menu changes. More of this packet, less of that drink, maybe a supplement added or removed. Your plate is basically personalised medicine. Long term, the only way to loosen that tight resupply chain is to grow food locally. But lunar soil is a hostile starting point for agriculture. Regolith has no organic matter, no living microbes, no insects or worms to break down waste into nutrients. It also contains metals and compounds that could be toxic to plants and to you if they move up the food chain. So early farming will almost certainly use hydroponics, plants growing in nutrient solutions, or substrates where regolith is heavily processed and mixed with safe binders and nutrients. Light for those plants will probably come from LED arrays tuned to the wavelengths plants use best, or from concentrated sunlight piped in through fibres. On the ISS, plant experiments have already shown that crops can grow in microgravity, but they behave differently. Roots don't know which way down is, cell structure can change, and their defences against microbes shift. In 1/6 G, we don't yet know how roots, stems and leaves will respond. Will tall plants be stable? Will water and nutrients spread evenly through substrates when gravity is that weak? How will plant diseases act in a closed, high CO2, low gravity environment? In your first year, any greenhouse module is still a pilot project. Yields will be small compared to your shipped food, but the stakes are high. Fresh leaves, herbs or fruits bring vitamins, variety, texture and smell that vacuum-packed meals can't match. A single fresh tomato or a handful of lettuce in a place with no natural life outside can have a real psychological effect on the crew. At the same time, those plants share your atmosphere. If something goes wrong, mold outbreak, pest contamination, unexpected allergens, it affects the same air you breathe. So just staying alive on the moon is a physics and biology puzzle running 24/7. You're drinking water that has already been through you once. You're eating food that was launched at huge cost, supplemented by fragile early crops. You're exhaling into machines that have to turn your waste back into something you can use. Any sustained failure in that chain is not just an inconvenience. It is a countdown to when a resupply ship must arrive or when you have to leave. And while your body depends on this tight loop of matter inside the base, your mind depends on something even more fragile coming from outside. Delayed, filtered signals from Earth that are your only link to everyone you left behind. If your food and water loops are this stretched, what happens to your head when even simple conversations with home break into awkward delays? and you realize you're not part of Earth's real-time world anymore? Talking to Earth from the moon sounds simple. Point an antenna, send a signal, get a reply. In reality, even the physics gets between you and the people you care about. Radio waves travel at the speed of light, but the moon is about 380,000 kilometers away, roughly 240,000 miles. That distance means about 1.3 seconds for your voice to get to Earth and another 1.3 seconds to come back. A 2.6 second round trip does not sound like much until you try to have a normal conversation with it. On Earth, you interrupt, you react mid-sentence, you cut in with jokes or questions. Your brain is tuned to sub-second timing. With 1.3 seconds of silence after everything you say, the rhythm breaks. You say something, you wait. They start to reply, but by the time you hear it, anything you added in the meantime risks overlapping. So you start speaking in blocks and then forcing yourself to stop. Jokes land late and feel flat. Emotional moments get chopped up into careful, slow statements. During Apollo, crews already reported this strange feeling of always waiting for Earth to catch up. On the moon for a year, that becomes the default way you talk to almost everyone who is not standing next to you. That same delay moves into your daily work with mission control. You report a problem, they hear it 1.3 seconds later, they ask a question, you hear it 1.3 seconds after that. Quick back and forth troubleshooting turns into a more formal pattern. Send a full status report, wait, get a block of instructions, answer questions in batches. It works, but it's not like having a flight controller in your ear in real time. In an emergency, that gap feels huge. Even when the timing works, the connection itself is not unlimited. Early lunar bases will have high-gain antennas and maybe relay satellites in lunar orbit, but you're not getting fiber optic speeds. Your link has to carry video from cameras, telemetry from life support systems, scientific data, navigation and tracking, plus voice and text. In quiet periods, you might have decent bandwidth for video calls, file transfers, maybe some entertainment. During heavy operations, a big EVA, a rover sortie, a landing or departure, mission data takes priority. Your personal connection back home can get throttled or even paused. That means your experience of being online in year one may sometimes feel closer to a slow, high-latency satellite link than to the broadband you're used to. Buffering on video, restrictions on when you can make high-bandwidth calls, schedules for large file uploads and downloads, social media feeds that are pre-cached instead of truly live. You will adjust, but it's a sharp reminder that you're living on the thin end of a long, narrow data pipe. Everything that reaches you from Earth passes through that pipe, and it is not just slowed, it is filtered. Messages are delayed by at least 1.3 seconds, one way, but in practice much more, routing through networks, queuing and sometimes human review. News from Earth comes in chunks, daily summaries, edited video, selected headlines, not the constant background noise of notifications and live streams. Live sports, always slightly delayed. Big world events, you may hear about them minutes or hours after everyone on the ground does, depending on schedules and priorities. And there is another layer. For crew health and mission focus, ground teams will sometimes curate what you see and when you see it. If something extremely stressful is happening at home, they might time the message for when you are off duty, not about to start a spacewalk. So your view of Earth is not just late, it is organized. You feel that. You know you are not part of Earth's real-time conversation anymore. In the first year, before you have a solid lunar normal, that sense of being slightly out of sync with everything and everyone you left behind hits hard. At the same time, the communication delay forces a shift in how decisions are made. On the ISS, there is already a trend toward more crew autonomy, but controllers can still talk back almost instantly. On the moon, that delay and the harsher environment mean you and your crew must own more real-time choices. You can't wait several back and forth cycles every time a valve behaves oddly or a rover wheel slips. You will decide which system to stabilize first, when to turn back from a risky EVA, how to improvise a tool from what you have on hand. That autonomy is satisfying in one way. You're not just a remote-controlled robot, but it also adds mental load. Every decision carries real consequences with less chance for immediate outside confirmation. You still get procedures and big picture guidance from Earth, but more often you'll be the one adapting those plans on the fly. Astronauts already report procedure overload and decision fatigue in low Earth orbit, where the environment is easier and help is closer. On the Moon, with higher stakes and less backup, that pressure is higher. In Year 1, there is also no long history of best practices yet. Many of your choices are the ones that create the rules for future crews. When you first arrive, contact with Earth feels exciting. Media interviews, first calls with family from the lunar surface. How does it look? How does it feel? Every conversation carries novelty. People want to hear from you. You want to share every detail. Over time, that peak fades. Life settles into routines. Maintenance, experiments, exercise, housekeeping. Calls home become something you squeeze in between tasks and sleep. They are still important, but they compete with exhaustion and the need for downtime. By month 6 or so, your family's questions shift from "what's it like" to "how are you holding up?" And even those talks are shaped by time slots, bandwidth and delays. Some days you will feel too drained to fully open up. Some days they will be busy with their normal Earth problems of work, school, traffic that do not line up with your schedule of EVAs and alarms. You start to feel the distance more, not less. The novelty of "I'm talking to someone on the Moon" wears off on both ends, and what's left is the reality. You live somewhere else now. That's the moment the psychological status flips. You're no longer just visiting. You're an expat from Earth with a different gravity, different sky, different day length and different risks. Your culture, your news, your relationships are now run through a thin, delayed link. The first year is when that change hits the hardest, because you remember very clearly what it was like to be fully inside Earth's flow of time and events, and you can feel yourself slipping out of it. And all the while, inside the base, you're not alone. You're sharing a small, sealed habitat with a handful of people you cannot walk away from, in a place where arguments don't just ruin your day, they can ruin the mission. If communication with Earth is already strained by distance and delay, what happens to your mental state when the only humans you can reach in real time are the same few faces you see every single day, with no exit and no real privacy? Living on the Moon means sharing a very small world with a very small number of people, and having no way to step away when things get tense. Early bases will probably have crews of maybe 4 to 10 people. That is closer to a big family than an office. You eat together, work together, exercise together, and sleep just a few meters apart, with only thin walls and doors separating you. There is no going outside alone to clear your head. Outside is vacuum and radiation. There is no changing apartments, no new co-workers, no commute. The group you launch with is, for many months, your entire in-person social universe. We already know from Antarctic stations and submarine deployments that even stable, trained crews in isolated environments form cliques, have conflicts, and build up long-running frustrations. Small differences in habits, one person is messy, another is loud, another likes to stay up late, become big problems when you can't get away. On the Moon, every annoyance is amplified by the constant background awareness that everyone's performance matters for survival. If someone is careless with checklists or always late to shifts, that is not just a personality quirk, it is a potential safety risk. It is hard to relax fully around people when you are always also evaluating them as teammates in a dangerous job. Psychologists see a common pattern in long, isolated missions. Things often feel okay at first, then drop sharply around the third quarter of the mission. In the beginning, there is excitement and novelty. Near the end, there is a clear finish line and the mood can lift. In between, there is a long stretch where the newness has worn off, but the end is still far away. That is when morale drops, irritability goes up, and small conflicts swell. On a one-year lunar tour, that third quarter is not a few days. It might be several months. Early on, you are too busy and too fascinated to notice much. Setting up equipment, exploring your surroundings, sending first reports home. By around month 4 to 9, the thrill has faded. The daily view has not changed. Work has become routine. The return to Earth is not close enough to feel real. This is when every flaw in your crewmates' personalities seems louder. The way someone chews, the jokes another person repeats, the tone a commander uses when tired. You know intellectually that this is a psychological phase, but that does not make the emotions feel any less sharp. At the same time, you are dealing with a strange kind of culture shock. The moon has no native language, no local food, no holidays. Everything you bring into movies, music, recipes, games comes from Earth. But it does not fit perfectly because the environment is so different. A movie about walking through forests feels more alien than any science fiction, because you have not seen a tree or felt wind in months. Food traditions based on big ovens and fresh ingredients don't translate well to reheated pouches and small appliances, so you and your crew start building your own tiny culture. Maybe there is a certain night of the week where you always eat a particular meal and watch a certain show. Maybe you mark lunar landing day or base day with special decorations or a different work schedule. Maybe you develop running jokes about specific pieces of equipment or about how bad a certain dehydrated dish is. In year one, these rituals are awkward at first because you are still trying to copy Earth patterns. TV nights, game nights, casual Fridays. Over time, some of those experiments stick and some die out. A genuinely lunar microculture with its own habits, slang and rhythms will start to appear in later years. You're there before it really exists, trying to invent it while also doing a demanding job. Within that small culture, leadership matters a lot more than in most workplaces. On a long mission, the way a commander runs the crew can directly affect how well people sleep, how they handle stress, and whether conflicts stay manageable or blow up. An authoritarian style can be efficient in emergencies, fast decisions, clear orders, but over months it can cause resentment and silence honest feedback. A very flat, consensus-based style can feel more fair, but it can also be slow and indecisive when something critical breaks. Year one leaders do not have a long history of this is how you run a lunar station to lean on. They have training from space agencies, lessons from ISS, analog missions and polar stations, but no decades of lunar case studies. When something happens that doesn't match the handbook, a crew member quietly withdrawing, a conflict between mission goals and someone's health, a serious mistake, the commander is improvising. Psychologists on Earth can see some of the data. Mood reports, sleep patterns, conversation logs. They can advise over delayed links, but they cannot walk into the habitat, pull someone aside and read the room in person. The pressure on local leadership is constant. Then there is a layer of stress no other generation will quite feel the same way. The knowledge that you are the first group living this way. Every argument, every breakdown, every near accident feels like part of history. You're not just having a bad day, you're having one of the first bad days people ever had while living on another world. That thought can make small issues feel bigger and heavier. If you snap at a crewmate, you might immediately worry that you're failing the mission on some deeper level. If you forget a step in a procedure and someone else catches it, you not only feel personal guilt, you also know that incident will go into training slides for future crews. The base itself feels fragile in year one. The walls are thin, the shielding is still being built up. Life support systems have not yet proved they can run for years without major overhauls. Everyone knows deep down that a chain of bad decisions or bad luck could still shut the whole project down. Later crews will arrive to a place that feels established. More modules, more redundancy, more routines. For them, Moonbase will be a thing that already exists. For you, it is something that can still fail. That awareness colours every interaction. People hold grudges differently when they think a mission might be cancelled if relationships fall apart. So your first year on the moon means living in a sealed micro-world with a handful of people you cannot leave, under leadership still finding its style, in a culture that does not fully exist yet, with the knowledge that every mistake and every conflict is being watched, recorded, and learned from. You're testing not just hardware, but the basic question. Can a tiny human society stay stable and sane this far from home? And all of that is happening before you add real emergencies, fires, leaks, injuries, where the physics of vacuum and low gravity turn small faults into life or death events in seconds. If relationships are under this much stress in normal operations, What happens to the crew when things actually go wrong and you discover how unforgiving lunar emergencies really are? On the moon, a fire alarm does not mean everyone outside. There is no safe outside. The air in your habitat is limited, pressurized, and kept at the right mix for you to breathe. A fire eats that oxygen fast and fills the same small volume with smoke and toxic gases. You can't just vent the room freely either, because that air is precious and opening to vacuum too fast can damage equipment and people. Past disasters like the Apollo 1 cabin fire and the fire on the Mir space station showed how quickly flames in a confined atmosphere can turn deadly even when escape is technically possible. In a lunar base, your escape options are far more constrained, so your first-year crew will drill for fire in a way nobody has ever done on another world. You'll practice shutting hatches, switching airflows, deploying extinguishers that work in low gravity and enclosed spaces, and maybe switching the habitat to a different gas mix in an emergency. You need to move fast but not panic, because every action has trade-offs. Vent too hard, and you may depressurize parts of the station, respond too slowly, and you may lose a module. Early on, fire sensors, extinguishers, and ventilation controls are still being tested in real lunar conditions. You're validating how smoke actually moves in partial gravity, and how well your gear copes, with your own lungs and eyes in the middle of that experiment. Decompression is even less forgiving. A structural failure from a micrometeoroid strike, a bad seal, or a damaged hatch can drop the pressure in a compartment in seconds. Human tolerance to full vacuum is measured in tens of seconds before you lose consciousness, and only a couple of minutes before serious, often permanent damage. You don't explode, but gases inside your body expand, water in your lungs and on your tongue can start to boil, and oxygen in your blood disappears rapidly. Emergency designs assume you have backup doors, isolation valves, and fast-acting pressure suits nearby. On paper, it looks clean. Detect a pressure drop, close bulkheads, move people into safe zones, patch leaks. In reality, alarms might be ambiguous at first. A small leak might sound like equipment noise. A bigger leak could start while people are in the airlock or halfway through an EVA. You might be asleep when it happens. Every time you cycle through an airlock, you're trusting gaskets, hinges, latches, and software that have not yet been proven over years of thermal cycling and dust exposure. Every time you step into a suit, there is a non-zero chance of a manufacturing flaw or an unnoticed abrasion. In your first year, you are the first group to find out how often rare really is for these failures. Quick reaction drills, rehearsed emergency mask use, and automatic bulkhead closures are your only real buffer against the physics of vacuum. If someone gets hurt, sick, or exposed, your medical options are limited from the start. There is no full hospital on the moon, no emergency room down the street, no helicopter ambulance. You have a medical kit, some diagnostic tools like ultrasound and basic lab equipment, a small pharmacy, and maybe a space setup for minor surgery. You also have telemedicine links to doctors on Earth, but those links come with that same 1.3 second one-way delay and bandwidth limits. Routine problems, small cuts, mild infections, strains, are manageable. Serious issues are a different story. Appendicitis, a major fracture from a fall, a heart attack, a deep burn from a suit or hardware failure. On Earth, those mean ambulances, operating rooms, specialist teams. On the moon, each one becomes a high-stakes puzzle. Can you stabilize the person with what you have? Is it safer to treat them there or to prepare an evacuation? Even in the best case, evacuation is not immediate. You need a working launch vehicle, the right orbital alignment, and time for transit back to Earth. You're talking days, not hours. In your first year, every significant medical case is likely to push beyond what the original guidelines assumed. You're operating at the edges of known procedures, using equipment that have been qualified for spaceflight but not for full Earth-level emergencies in low gravity. The emotional impact of that is heavy. You know that if something serious happens to you or a crewmate, there may simply not be enough capability to do what would be standard in a terrestrial hospital. Behind all of this is the basic engineering trade-off between safety and mass. The ideal rule in harsh environments is 2 is 1, 1 is none. For every critical system, You want at least one full backup and sometimes a third. But every kilogram of extra pump, valve, wire, filter or processor costs launch capacity and money. Early bases will be fighting tight mass budgets. They cannot triple duplicate everything. That means your first-year outpost will live closer to the edge of just enough than any mature moon base later on. Maybe you have full redundancy for air circulation and power, but only partial backup for water processing or waste handling. Maybe you carry enough spare suit parts to handle a couple of major failures, but not a whole run of bad joints. Maybe the backup communication system can handle voice and basic telemetry, but not high bandwidth video. Later, after real operations, designers will know where they cut too close and add more margin. In year one, you don't have that hindsight. You find out which non-critical pump turns out to be very critical when it fails. You discover which spare you wish you had brought when a component that never fails in test dies 3 months in. And then there are the failures you haven't even imagined. Apollo missions ran into unexpected issues. Dust behaving worse than predicted. Tools that didn't work as expected in suits, biomedical effects that surprised doctors. A year-long mission multiplies the exposure time and the complexity by a huge factor. You now have continuous life support, complex habitat systems, surface vehicles, mining equipment, robotics, and human biology all interacting under radiation, dust, and partial gravity. Somewhere in that mess are unknown unknowns, failure modes that don't match existing categories. A chemical that outgasses from a 3D printed wall and poisons a sensor coating. A thermal expansion pattern that twists a docking ring just enough to cause leaks. Those effects will not show up cleanly in models. They show up as weird readings at 3 AM, as unexplained symptoms, as near misses. That is the real core of why the first year on the moon is the hardest. During that year, rules are being written, not just followed. Checklists are born from your mistakes, emergency procedures are patched after your scares, hardware redesigns are ordered because of your field fixes. You are living inside the experiment that will later look like standard operating procedure in manuals, but while you are there, the manuals are incomplete. And through all these emergencies and near misses, your body is also going through a slow, deep experiment no one has ever run, living for a year in 1/6 G, under constant radiation, inside a closed ecosystem, with microbes and cells and genes responding in ways we do not fully understand. If the physics of the moon can break your machines this easily, what is it doing over months and years to the biology you carry? Human biology evolved in one place only, Earth at 1G with blue sky, microbes and gravity all in a specific range. The moon offers none of that, yet you're asking your body to treat it as home for a year. That's not just a medical challenge, it's an experiment on every level, from whole organs down to gene regulation. One of the biggest unknowns sits in the background of any talk about settling the moon. Right now, we have zero human data on what happens if a pregnancy starts in reduced gravity, or if a baby grows up in it. Animal studies in orbit hint at real concerns. In microgravity, some embryos don't implant properly, some pregnancies fail, and the offspring that do survive can have changes in balance organs, muscle and bone development, and even gene expression. Partial gravity at 1/6 G might be less disruptive than weightlessness, but that is just a guess. Ethically, nobody is going to run deliberate pregnancy experiments the moment a base opens. But the second people live somewhere for a year at a time, the question stops being abstract. Can a fetus develop normally when down is so weak? Does the vestibular system, the inner ear balance hardware, wire itself differently if the pull it uses as a reference is 1/6 of what it is on Earth? Would a child born there ever be able to safely live in 1G? Or would returning to Earth be like moving to a world with crushing gravity? Your first year mission won't answer those questions directly, but every scan, every hormone profile, every data point on adult adaptation feeds into the models that will decide whether the moon can ever be more than a temporary camp. At the same time, you are not alone on a microscopic level. Your body and your habitat are full of microbes, your gut bacteria, skin flora, and all the environmental organisms that ride in on cargo, equipment, and people. On the ISS, crews have already seen that spaceflight changes these microbial communities. Some beneficial bacteria drop in number, some potentially harmful ones increase. Biofilms, slimy layers of microbes, can form inside water systems and on surfaces in ways engineers didn't fully expect. On the Moon, the sealed environment, the constant presence of dust, new materials like 3D printed regolith structures, and higher radiation all push these microscopic ecosystems into unknown territory. The microbes on your skin and in your gut are dealing with different diets, different hygiene routines, different stress hormones. Those on surfaces in the base are growing in air with lower humidity and different chemistry than a typical Earth building. Radiation can kill some microbes and stress survivors, driving genetic changes, so you'll be taking swabs from walls, air ducts, water lines, tablet screens, and your own body. Each sample gets sequenced or cultured to build a map of how the habitat's mini biosphere evolves over time. In year one, this isn't just academic. If certain bacteria that cause infections start to dominate, cleaning protocols change. If biofilms show up in water lines, filters, UV units, or chlorine dosing gets adjusted. Your living space slowly fills with a new ecological mix that has never existed before, and you're breathing and touching it every day. On top of that, your immune system is under constant strange stress. Spaceflight data already show patterns that worry doctors. Reactivation of latent viruses like herpes zoster, the virus that causes shingles, changes in how T cells function, shifts in inflammation markers. The likely causes are a combination of factors: disrupted sleep, chronic psychological stress, radiation exposure, altered microbiomes, and unusual fluid distribution in the body. Partial gravity may ease some purely mechanical issues, but it doesn't fix the stress, radiation, or isolation. Over a year, you might notice you catch small things more easily. Skin infections that take longer to clear, cold-like symptoms without an obvious cause, cuts that seem slower to heal. Allergic type reactions could appear in response to habitat materials, dust traces, or even new microbial mixes. Some of this will be subtle and only show clearly in lab data. White blood cell counts shifting certain cytokines signaling molecules, staying elevated, viral DNA appearing in saliva that indicates a dormant virus has woken up. Every blood draw, every saliva sample, every immune function test you run is feeding a new field. Human immunology and partial gravity and high radiation. In year one, clinicians won't fully know yet which changes are harmless adaptation and which are early warning signs of deeper problems. They will err on the side of caution, adjusting workloads, sleep schedules, and medications based on your data. Your eyes and brain are also in the experiment. In orbit, many astronauts develop spaceflight-associated neuroocular syndrome. The optic nerve head swells, the shape of the eyeball flattens slightly, and vision can shift toward farsightedness. The leading theory is that fluid shifting toward the head increases pressure inside the skull just enough to compress parts of the visual system. The big unknown is how much partial gravity helps. On the Moon, gravity isn't zero, but it's still weak. Does 1/6 G pull enough fluid back toward your legs to prevent those eye changes, or just reduce them? Will you see a milder version of SANS, or a new pattern entirely? Your first year will answer that with an uncomfortable level of detail. Regular eye exams in the habitat, photos of the back of your eye, visual field tests, and possibly MRI scans done before and after the mission will show whether moon eyes become a standard risk. Any persistent blur, headaches behind the eyes, or changes in visual acuity will be taken very seriously. Because once you've lived in low gravity for years, fixing that kind of damage may not be easy. Deeper still, your body is adjusting in ways you can't feel at all. Epigenetic changes. The NASA twin study, tracking one twin in orbit and one on Earth, showed that long-duration spaceflight can alter which genes are turned on or off, and how DNA is packaged in cells. Some of those changes reversed after return, but some persisted for months or longer. That's not your genes mutating, it's the control systems around them rewiring in response to environment. A year on the Moon adds new inputs to that system, different gravity, constant low-level radiation, a contained microbial environment, a highly controlled diet, chronic stress. Blood and tissue samples from you will reveal shifts in gene expression across immune cells, bone and muscle markers, and maybe even brain-related genes. Methylation patterns, chemical tags on your DNA that affect how it's used, will likely shift. You essentially become the first version of a human whose molecular history includes lived 1 year off-world in partial gravity. Whether those changes turn out mostly reversible or partly permanent is not clear. They could be neutral, harmful, or even beneficial in some ways, making you better adapted to lunar conditions at the cost of being less comfortable in 1G. That's part of what makes the first year so high stakes biologically. You are not just testing whether you can survive 12 months. You're testing what kind of human comes back after 12 months, and whether large-scale settlement would slowly create a population biologically tuned to the moon more than to Earth. And all of this deep biological experimentation is happening while you try to do basic tasks like sleeping, working, and walking through halls that are still being bolted together. Your cells, microbes, and organs are adjusting in ways medicine is barely starting to track, at the same time as your base is physically growing and changing around you. If your own body is this much of an unknown in year 1, what does that say about your living environment, when the very walls and systems that keep you alive are also prototypes being assembled in real time, turning your home into a construction site where every mistake has immediate physical and biological consequences? On the moon, you don't move into a finished base. You move into the first working module, and then build the rest of your house around you while you're living in it. That means your home is a construction site for most of the first year. You sleep a few meters from walls that are still being bolted together. You eat while hearing pumps, drills, and fans spin up and down. You step out of your bunk and find a new cable route or a temporary barrier where there wasn't one yesterday. Outside, you spend months in suits moving regolith, laying power and data lines, anchoring structures, and assembling new habitat sections. Inside, you deal with noise from compressors, fans, pumps, 3D printers, and test rigs. Vibration travels through the rigid structure, so a tool running in one module can shake walls in another. Dust from construction wants to sneak in every time the airlock cycles. Layouts change as modules arrive and get connected. Home keeps shifting shape while you try to run a stable life support system and a research program. A big part of that construction effort is learning how to turn lunar regolith into something you can actually build with. Plans call for using in situ resources, sintering regolith with focused sunlight, or microwaves to fuse grains into solid blocks, or 3D, printing it into walls, tiles and radiation shields. In theory, this saves huge amounts of mass because you're not launching bricks from Earth. In practice, regolith is not simple sand. It's a complex mix of crushed minerals, glass, and tiny bits of metal, including iron in forms that can be very reactive. At high temperatures in vacuum, regolith can chemically attack crucibles, heaters, and electrodes. Without air, heat doesn't move the way it does in a furnace on Earth. There is no convection, no hot air rising and cool air falling. Heat moves only by direct contact and radiation. That makes temperature control tricky. Parts of your 3D print might overheat and crack, while others stay too cool to fuse properly. In year 1, you run real-scale tests on the surface, not just in labs. You might fire up a microwave sintering unit and discover that dust nearby melts or charges differently than expected. You might bake a wall and find fine cracks after a few thermal cycles between lunar day and night. You might learn that certain regolith compositions near your base are more corrosive to your metal components than the simulants used in testing. Baking the moon into reliable, long-lived structures is no longer an engineering slide. It's a day-to-day learning process with your own shelter at stake. To reduce human exposure to dust, radiation, and fatigue, you lean heavily on robots as co-workers. Small bulldozer-like machines push and pile regolith. Haulers move containers, printer units lay down layers of material. In principle, this saves EVA time. In reality, in year 1, you're teaching these machines how to behave in real lunar conditions. Teleoperating a rover from inside the base or from Earth sounds straightforward until you add the 1.3-second delay in rough terrain. You move a joystick, wait, watch the rover respond on a slightly lagged video feed, and by the time you see that you're about to clip a rock or cable, your last command is already in motion. Tip-overs, minor collisions, and misaligned placements are almost guaranteed early on. Autonomous navigation and construction software can help, but they introduce new failure modes, misinterpreted sensor data from dust, bad decisions around soft or sloped ground, path planning that doesn't account for how regolith behaves when disturbed. In your first year, the rate of robot accidents will be highest because every scenario is still new. You'll run rescue EV as for stuck rovers, dig out wheels buried in loose soil, and physically realign modules or shield blocks that robots placed a few centimeters off target. Every dumb robot move costs you suit time, energy, and risk, but each one also teaches you how to refine control software, routes, and safety margins for later operations. All of this construction sits on top of infrastructure that must never fail: power. Your life depends on solar arrays or nuclear units, energy storage, and the network of cables and converters that tie everything together. Early on, solar fields may be relatively simple. Panels deployed on the surface, perhaps on masts or short towers, connected by cables that are only shallow buried or even lying on the surface. Dust will slowly coat panels and cut their performance. Temperature swings will stress mounts and connectors. Cables can be damaged by thermal cycling micrometeoroids or accidental rover hits. As you expand, every power upgrade, adding new arrays, stringing new cables, bringing additional batteries or fuel cells online, means temporarily changing a live system that you cannot shut down. You reroute loads, disconnect and reconnect panels, and integrate new hardware while everything else in the base is still drawing power for air, heat, water, and computing. Mistakes here can cause brownouts or surges that upset sensitive life support or medical equipment. In year one, you have the smallest crew, the least spare capacity, and the most power work to do. That is when you are operating closest to the edge of one mistake away from lights out. Human factors design is another area where the gap between blueprint and reality shows up fast. On Earth, teams will simulate workflows, paths, and acoustics. They'll try to predict how people will move through the base and where equipment should sit. But they can't fully reproduce 1/6 G, the sound of real pumps and fans in that specific structure, or how dust and cables will actually route once you start improvising. So you arrive and immediately start noticing mismatches. A doorway is technically wide enough, but awkward for someone in a thick undergarment or with medical gear. A storage cabinet everyone uses is placed where you have to twist uncomfortably in partial gravity to reach it, stressing your back. A pump mounted on one wall sends a low-frequency vibration that resonates right through the metal near the crew bunks, making sleep harder. A workstation faces a window where direct sunlight during part of the lunar day blinds your screens, or cold from the wall makes the area uncomfortable. In year one, you don't have spare modules lying around to fix these things. You hack the base with what you have. You move equipment, reroute cables along paths that make more sense once you see real foot traffic, tape foam or insulation over noisy panels, hang improvised sound dampening. You rearrange storage so frequently used items are near the airlock, not the back of a distant rack. You put markings on floors and walls to guide safe paths around protruding valves or low fixtures. All of that takes time away from planned work, but it's essential if you want to keep people efficient and mentally stable. Later generations will inherit a much more polished environment. Module designs will incorporate all the feedback you send home. Noisy equipment will be isolated better. Doorways will be sized for real suit movements. Storage will be laid out based on actual use patterns. New sections will come pre-built with human-factored layouts. They will get the renovated, optimized moon base. You get the half-finished version: cables on floors, temporary braces in passageways, ad hoc fixes on walls, robots learning not to crash into things, and constant construction noise vibrating through your thin habitat skin. You cook, sleep, argue, and recover from EV as in a place that never quite feels settled, because objectively, it isn't. And somewhere in the middle of that constant building and fixing, your own mind starts to shift. You stop seeing the base as a temporary project and start seeing it as home with all its flaws. You stop feeling like a visitor and start feeling like someone who lives on the moon for real. That psychological line, where it's no longer a trip but you're normal, might be the strangest and hardest transition of all. If living in a construction zone on another world is this intense in the first year, what does it do to you when that year changes your sense of gravity, of home, and of what normal life even means? And when you realise you may never really see Earth the same way again? At the start of a one-year mission, it feels like a trip. You tell yourself you're an explorer on assignment going there and back. That story works for launch day, first EVA. First look at Earth hanging in the black ski does not match the feeling of brushing your teeth in 16G for the 150th morning, arguing over who cleans the air filters, or waking up in a bad mood and still having to put on a suit to fix a jammed valve. Somewhere in that first year, without one clear date, the moon stops being a destination in your mind and becomes the background of your normal life. That crossover is strange because nothing dramatic marks it. You just notice that your brain has stopped silently comparing everything to back on Earth, all the time. The cramped galley, the noise of the pumps, the lag in calls home, they move from temporary mission conditions to this is just how my days work. You plan weekend routines around the lunar schedule. You have favourite corners of the habitat. You recognise specific rocks and craters outside as landmarks. At that point, saying I'm visiting doesn't feel accurate anymore. You live there, even if the ticket home is already printed. As that shift happens psychologically, your sense of gravity itself rewrites. After months at 16G, your body and brain start treating that as the default. Your muscles adjust their automatic force. Your inner ear and balance system tune themselves to the weaker pull. The effort it takes to stand up, sit down and move feels normal. You may still remember 1G intellectually, but it becomes a memory, not a daily experience. When you eventually go back, Earth hits you as an extreme environment. Astronauts returning from just a few months in microgravity report that standing feels like work. Walking is tiring and some failed when they try to get up too fast. After a year of your nervous system using 16G as its baseline, 1G is not normal. It's 6 times heavier than normal. Your heart has to pump harder. Your circulation has to fight stronger pooling in your legs. Your bones and joints suddenly carry loads they haven't seen in a long time. You might feel like someone who's been living at high altitude and then drops to sea level, only in reverse. More weight, more strain, more effort just to move. That change doesn't fully go away. Your brain will adapt back to Earth, but your reference points will be different for the rest of your life. You will always know in a direct physical way that weight is not a fixed property of you. It's an environmental setting. You've lived with your body turned down to 1/6 and turned back up to 1, and that experience is hard to unlearn. Physically and mentally, the first cohort will come back with both scars and new strengths. Bones will show measurable changes, density loss in some areas, remodeled structures in others. Radiation badges and blood tests will carry markers of doses far beyond what most Earthbound people ever get. Microbiome samples from gut and skin will show community shifts that formed only in a sealed lunar ecosystem. Coping patterns for stress, isolation, and constant low-level danger will be different from what you see in people who've only worked in offices or even on the ISS. Some of these changes will be negative. Higher long-term cancer risk, joints that aged faster than they should have, memories of close calls that stick like trauma. Others will be more like new capabilities. The first-year crews will have an intuitive sense for how low gravity affects motion fluids and tools that no simulator can teach. They'll know which fears were overblown, which systems turned out more robust than expected, and which dangers were underestimated, like a specific kind of leak, or a particular dust failure, or a type of exhaustion nobody modelled correctly. They will have instincts about what feels off in a life support system, or work schedule that later generations, raised in more polished bases, won't automatically have. At the same time, your daily life will have turned something out of science fiction into routine infrastructure. For more than a century, living on the moon was a plot device. During your first year, it becomes a spreadsheet topic. Medical teams will turn your headaches, your sleep logs, your bone scans, and your eye exams into updated health guidelines for partial gravity. Engineers will turn your construction mishaps into building codes and safety margins for regolith structures and pressure modules. Radiation experts will use your dosimeter data to refine limits and shielding requirements. Policymakers will look at your psychological and social data, conflict reports, mood trends, communication habits, when they draft rules about crew size, rotations, and family contact for future outposts on the moon and on Mars. If, decades from now, anyone writes rules about having children off-world, those will draw heavily on the biological data you generated without ever being part of such a decision yourself. Your bad days, your small injuries, your fatigue and recovery curves become tables and graphs in training manuals and textbooks. That is part of why the first year is uniquely hard. Every major problem we've talked about, gravity changes, bone loss, dust, radiation, temperature extremes, psychological strain, construction hazards, unknown biology, hits its steepest learning curve then. Afterward, others will know which exercise routines actually hold bone loss down in 1/6 G, which materials survive thermal cycling, which dust control protocols truly work, which lighting schedules protect sleep, which leadership practices keep small crews stable. They will throw away what failed for you and standardize what worked. You don't get that benefit. You are the one testing all of it at once. You suffer through the broken sleep while lighting is tuned. You breathe the air while materials outgas and filters are swapped. You do the extra, risky EV while robots are still unreliable. You endure the clumsy early habitat layouts before human factors fixes arrive. You are the one who finds out in your own body how much radiation a year on the surface really delivers, and how much gravity is just barely enough to keep a human frame functional. But that first year also has to happen. Without it, settlement never moves beyond talk. The only way to know if a world is livable long-term is to put real people there long enough for all the slow problems to show up. Skeletal aging, immune drift, dust disease, mental burnout, hardware fatigue. A few days or weeks can't reveal those. A year can. If we get through that first year with people healthy enough to come home, systems stable enough to trust, and lessons clear enough to improve designs, then the question about the moon changes. It stops being can we really live there, and becomes how many, how big, and where next. That shift doesn't just affect the moon, it sets the pattern for Mars and for any other place we try to turn from target into home. The price is that someone has to live through the hardest version first. That's what the first year on the moon really is, the most intense, compressed test of human biology, psychology, and engineering we've ever run. Not in a lab, not in orbit, but on another world's soil, with no pause button. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.